I think it's time to get started with our next talk. We have Jorge and Yury from ASML talking about how to put Julia in an expensive machine.
Yes, thank you
Over
very
to
much. Okay, thank you. Thanks everybody for coming. This is actually my first technical talk at JuliaCon. Not my first talk, but first technical talk. So I'm happy about this. So first a quick intro. So I'm Jorge Vieyra, in case you don't know. I'm a lead functional engineer at ASML. We call functional at ASML people that are into the domain knowledge, domain-specific knowledge, algorithms, physics, math, whatever. And Yury here is a software architect, although his background is in neuroscience, I think. So he probably knows more about algorithms than I do. But he's on the software side, and we're usually, we're two sides of the same coin at ASML. He works on the software side of things, and I work on the algorithm side of things. And you know, with Julia, we want to blend these things together, but that's how it happened at ASML. I'm not going to introduce ASML because it has done it before. We had a keynote, very extensive keynote last year explaining what ASML does. So here's a link, you can look for it. But what I will going to explain is a little bit how a chip looks like. So I took this image from Wikipedia. And you can see this is a cross-section of a device. Well, it's a schematic of a device. And you can see it has several layers. That's how chips are built. They're not printed in just one soup. They're built on layers, upon layers. And usually the lower ones, what we call the front end of line, are the most advanced layers. The layers are made with the most recent advances of photolithography and process nodes and stuff. That's where the actual transistors are. And those are the most expensive layers. And as I said, made with the latest machines. In the case of ASML, there will be the EUV machines. Maybe you have heard about those. Then the intermediate layers are done in older, previous generation technologies. Also advanced, but not bleeding edge as the front end of line ones. And then all the way to the back, you will go for more mature technologies. And maybe you can see here that feature sizes start to increase as you go to the back end of line, as it's called. And at the end, you end up with a connector. This might be something that you can actually solder into your computer. Those are your connection pins that you might be able to see on your package. So that's how a chip is built. And I know that in recent years, we have been talking about UV machines that have been on the news because they are the most advanced and blah, blah, blah. But we also have other very advanced machines that are previous generations, but still kind of good. So we have the twin scan machines, so the immersion machines. So that's our previous advanced machines. And we also have what we call dry machines. So I just put a couple of those over here so you can have an idea. And as I said, we usually talk about the nanometer resolution of each of the machines. So EUV has this 8 nanometer resolution, took this from the website. The previous one has a 38 nanometer resolution and the all dry 110 nanometer resolution. That sounds big, but I mean, it's very small still. But the important part is not, the important metric for us is not the resolution, but this other metric over here, on how many wafers per hour it produces. You can see that the very advanced machine is fast, but it's not the fastest one. It produces 185 wafers per hour. But the previous nodes produce like 310 in this case, or 400 in the dry system. So they're like producing pancakes. They're really fast. And why is that important? Well, if you focus on the immersion ones, which tend to be the ones that we benchmark with, they produce roughly 300 wafers per hour. I'm rounding things up. This, by the way, is an animation of how our twin scan system works. It's measuring one wafer at a time while it's exposing the other one. But each time it exposes one wafer, one field at a time. It has roughly 100 to 300 exposure of those. Each exposure might have 1 to, I don't know, 12 dyes, depending on the reticle size. And that means that each wafer is exposed roughly at 12 seconds per, we have a wafer every 12 seconds or so, which means each exposure takes 400 milliseconds. that means that we only have like 330 milliseconds or so of calculation time. Where did the other 10 milliseconds go? We don't know. So, but we have, that's our budget. And we have to make all our calculations within that budget. Because, well, as I said, they have like, let's say 100 exposures per hour, 1 chip per exposure, $50 per chip. That's roughly 1 million or something, 1.5 million per hour. So this is basically printing, they're printing money machines. So we want to be able to make those exposures as fast as possible, increase the yield as much as we can. So that means that the algorithms that come into optimizing these exposures to increase yield, make things better, are becoming increasingly more complex. And we only have 30 milliseconds. So that's why we have to do this. And we, of course, customers want to have this not today, but yesterday. So we have to deliver as fast as possible. And that's why we look into the Julia programming language. Again, this slide has been shown in previous JuliaCons. We're just going to go through it. So we have an idea. It's usually the case that we have a prototype. And these prototypes are usually made in Python, MATLAB, whatever. Now we want to do it in Julia, because when you have the prototype, you want to immediately put it as a code, as a product code. And traditionally, that's rewritten in C, C++, whatever, and you put in an equipment. In this case, we're focused on these twin scan machines, and that's what we want to do. And we say, okay, fine, how can we actually achieve that? Can we make a proof of concept on how to make a Julia calculation that has to interact with the rest of the machine, which is already written in C, C++, so it doesn't come in a vacuum. The algorithm is in Julia, but we want to deploy it there. And we have certain restrictions for that. So we have to be fast, of course, but also very, very important, has to be consistent. I mean, garbage collection calls are not allowed. We cannot wait for Mackie to finish compiling. So it has to be like, everything has to be pre-compiled ahead of time. We're not using Mackie, by the way, on the scanner. So everything has to be compiled ahead of time, no JIT, and everything has to be very steady, and we have to interact with our interfaces. So those are our requirements. We have an extra one, is that, okay, we can do that with package compiler, but package compiler has a large binary, so that's why we want to get away from that, and also we want to be able to reduce the reverse engineering aspect to it. So package compiler also has a lot of metadata including that. So that's why we look into using what we call Julia C. Here we call it trim. ASML, some other people call it the static call graph. I will use these 3 terms interchangeably, but we all talk about the same thing. So we have been working with Julia Hub for some time now. I think like more than a year and a half or so, almost 2 years. With this feature. So let me just show you one toy problem that we look at. We said, okay, let's use some Czernike polynomials. That's something that we use thusly at ASML. So these are, if you don't know, these are polynomials that fit round things. So like a wafer or a lens. So those are things that we have. Usually people just show these circles, which are the monomial terms for the polynomial, and they fit those kind of weird geometries on a wafer. So if you add enough of those, you can feel weird shapes on a round domain. So we usually use those. We thought, okay, let's use something that's kind of reasonable that we can just measure on the wafer. We can expect 100 measurement points and a 7-order Czernike polynomial. That's like 76 monomials of this. So we want to have something that's kind of representative, and we put that as a proof of concept on our machine. And we asked the software guys, and they say, okay, you have like roughly 1.5 milliseconds of budget to do this kind of calculation. So as it happens, I wrote some code for this some years ago and said, okay, here it is. Please, software guys, please take my very fancy fast Czernike code and in Julia and try to make a proof of concept. Say, okay, we need to make a binary size. At the time, they could not do it, but okay, we will say, okay, just make the Julia code. And one extra restriction I forgot to mention is that because these systems are also running on some legacy platforms, AVX512 is not allowed, among other things, because also AVX512 overheats the CPU, and then this variability is quite high. So that's not allowed. It's like one restriction that we have, no AVX512, which is kind of sad. So I'm just going to quickly show you two kind of benchmarks, just benchmarking the Julia algorithm itself, and then when we interface with the TwinScan, also benchmark that, because the interfaces, that code also might generate some overhead. So I will focus on that. First on the algorithm. So as I said, I gave these Cernic polynomials module to the software guys. They made a proof of concept. They came back to me and they showed, I don't know if you can see this plot. And they say, yeah, well, it's kind of on the budget, but it has these weird regimes and calculation times. It's usually fast, but then sometimes it's not so fast, and then there are some outliers that go out of budget. So what's going on with your algorithm? It's like, it's not steady enough. By the way, this is running in a simulated system that has the same run characteristics. So if it's produced with this calculation time over there, that's what we expect. So this is what the scanner will see. Let's see. So like, okay, let me take a look. I cannot test it in these machines that are limited. I can test it on my Windows machine, so that's very noisy. So that's the noise. That's why you see the same. This is the same plot, but with my noisy Windows machine. This is also the scales a little bit different. It's logarithmic scale, but never mind. You see, that's also noisy. It has several regimes on the calculation time, and also has some outliers. On top of those outliers, I thought, okay, I'm just going to get from benchmark tools which ones are GC times, and those are the points in orange. So I thought, okay, if I get rid of those, probably I can get rid of those outliers. So start to work towards reducing those allocations, so reducing allocations, dynamic dispatches, and so forth. And eventually got it, like, was almost there, and by myself, I was almost able to get rid of all of them. Hopefully, Gabriel helped me, and then I was able to get rid of Baraldi from Julia Hub, and he helped me to get rid of all the final allocations, so it was no allocations done with this Cernic code. So I was really happy about that. So I said, okay, let's benchmark it, and it was kind of okay. So I was happy with that, but let me just quickly explain what I did to get rid of those allocations. So of course, I got rid of all the abstract types that were kind of plaguing my implementation. It was one of my first Julia modules. I put some tuples which had variable size, just made them fixed size, too bad. I was able to use infinite number of Cernic terms, but that was kind of unfeasible with my design. So, okay, so if I have only 200 and something, that's twice the amount of Cernic that we use, so that's good. I convert a lot of broadcasts to loops, because just using loops is awesome. And I removed several allocations, change things to if else instead of dynamic dispatches, and used one thing I wanted to use from the very first time. The very first thing when I wrote this thing, is generated functions. At the time I didn't know how to write them, but now I know enough to write those, so I was quite happy. And that's how we got rid of most of the allocations. One thing I have to remark is that I used loop vectorization before. I was a fan. I'm not a fan anymore. For a very reason that it always forces AVX512, and you cannot get rid of that. And that was like, oh, super annoying. So I got rid of loop vectorization. I still use vectorization in base, but I still had to rewrite a few internal packages. I haven't upstreamed them, but I have to have my own implementation of CPU summary and host CPU features, because it has a lot of dynamic stuff with evals. So I was very unhappy with it, but okay, that's what I'm using. And also found out that sometimes Vue generates inefficient code, so I have to get rid of some of the views. So maybe that's for the Julia compiler guys. And also, not super happy, but to get rid of some of the GC calls, I have to use pointer arrays, so it was some manual memory management. At least I was happy that I was able to do something about that. These are some examples of things that I did, probably you can see them. I removed some integer, abstract integer types that I had on my structs to just int. Also, as I said, I just made this tuple fixed. Also got rid of some of the allocations. Instead of using tuple, which returns a variable size, you use fixed to end tuple. And there are several examples of that. I will not go through all of those. It was basically what I did. How I found this, well, at the time I didn't know that Jet could do that, but I found all of these dynamic allocations and stuff with a log check, and that's how I made the thing also Trim compatible. So I was quite happy about that. So now, these are just the things that we found for the algorithm itself, but we have to interface it with the machine, and for that, Yury is going to explain what needed to be done.
Yes, and the first problem that we had with integration to the machine is actually a decision. Do we put it as a just algorithm that we can call, or it should be tightly integrated? And we have a lot of interfaces in our code base. It's a really huge code base, over 50 million lines of code. And we said, okay, it's unfeasible that we will rewrite everything to Julia. And it's also unfeasible that we will keep writing only algorithms which are endpoints, so they don't depend on anything. And because of that, we said, okay, Julia should be like first-class citizen in our system. So it's not only called by our machine, but it's also calling it back to call some other algorithm to retrieve some data in real time. And that was the first reason why we said, okay, it should also communicate to it. It's tightly integrated. And the other problem, of course, our tight timing budgets requires that we don't copy data too much. We process a lot of data we can't afford copying it around. So the memory's safety, if we pass data by reference, was really important for us. Second was biggest question from all software architects who didn't work with Julia was like, okay, Julia is not similar to C or C++, that's the majority of our code base. It have garbage collector, so what does it mean for our performance? Can we even achieve reasonable performance even if our algorithm works well? It still uses garbage collector, and indeed how Jorge showed, for some algorithms you can get rid of garbage and so you don't need garbage collector, but yeah, in theory, you cannot do this for any algorithm. So that was a big thing. And the third problem was, how do we actually implement the static call graph? It was the first time when we started this discussion, static call graph was on horizon, and we actually started doing this work, even didn't know that the static graph will work, and that was a really nice collaboration between ASML, Julia community, and Julia Hub to make it happen. Let's go from the problems one to each other. Memory safety and pass by reference. I had a talk about it yesterday. I will not go in the details. All right, let's wait for a bit. All right, so pass by reference, how we solve the problem, how we are able to pass data allocated by C directly in Julia and work with it without any copies. And by the way, if you look here, this is a real life example, and you cannot see any unfamiliar Julia instructions or syntax except the first line. Yeah, because it's also transparent for our developers. Yeah, I had a talk about it yesterday. Please watch it. It's online. Second problem, garbage collector. Well, it's the biggest thing. But actually, it's not. What we found through our testing that you can even live with the current implementation of garbage collector. It's quite good. I will show you results on the next slide. But our main intake of this study was optimizing for garbage collector is actually not really necessary. You should not really worry about this. You should worry first about your code, what kind of algorithm do you run, what's the performance of this algorithm. But if you will optimize for a garbage collector later in your process, you will get additional performance. But if you feel that you are not capable or you have no time for this or it's too difficult, you actually don't get probably too much. Anyway, there is a couple of other strategies how you can deal with garbage collector, and let's look at them. So this is the first one is exactly the algorithm that Jorge described, but we plugged it in our interfacing system, and as an implementation detail, our interfacing system actually always produces just a bit of garbage. It's just a few extra objects, but for every call. Here we have a lot of calls. And we see that some of them are actually exceeding our time budget of 1.5 seconds, but actually not that much. The amount of the calls is really minimal. For us, it actually doesn't really matter, so we can live with the existing garbage collector, and the average time was around quarter of a millisecond, so, which is totally acceptable. But we thought, okay, what if we have other situations? And we thought about this idea. What if we just disable, because our algorithms here is very small, it's very fast, it doesn't produce a lot, so we can just disable garbage collector, we can do our computation, and then we force garbage collection, right? So instead of having the random spikes somewhere around our code, we have a guaranteed spike end of our code. Okay, what does it mean? Here's the test for the full collector, right? So the garbage collector of Julia supports the full garbage collector and the short garbage collector. Here's our results. It's still fitting the budget. So which is actually a very interesting observation, right? If you look at these two graphs, the left one and the right one actually do exactly the same computation and produce the same amount of garbage, but because the garbage doesn't accumulate, you never have this full strokes which takes time over the budget, which is very interesting, except the outliers. What's about outliers? Well, we found it by experimentation that garbage collector takes time to settle down. This is the procedure that we use to preheat it. Apparently, even that is not enough. And I just decided, okay, we'll leave it here to warn you about this. The start of your system will require a garbage collector to settle down. Once it's settled down, it's quite reliable, quite stable. There is still some noise, but it's probably noise of the system, not the noise of the Julia, right? And in our case, we don't produce long leaf objects, actually. Everything which we produce can be disposed at the spot, and then you can just use short garbage collector, which is working really fast, which works much faster, and you get the really acceptable timings. There is a lot of extra space to put your more computations, to make your algorithm more complex. But what if you are not happy with that, right? What if you really need to produce a lot of garbage every call, and you cannot deal anything with that? Well, there is an alternative strategy. You can stop, you can think outside of the Julia now. You can think about, well, my Julia is just a part of a bigger machine, and the bigger machine is doing client-server interactions in some way, right? And in this case, let's look at the timing diagram, right? The client is sending a request for the server to process, and the server is busy with processing it, and then it's busy with garbage collection. Let's assume it like this. Garbage collection can happen in the middle, but it doesn't really change anything. What if we say we disable garbage collector, right? We do the computation. What if we're able to return the data before we start garbage collection, right? What if our server allows it, and apparently most of the server implementations do allow you to postpone some action and return the result to the client before taking this action? Then you have such a timing diagram, right? Again, this is just an example. And the only difference is, well, you have this extra gap, but the client gets the result much earlier, so you actually don't see anything from the garbage collector on your client side. You just don't see it, and indeed server takes a little bit extra time, but usually with the correct implementation, this is like really peanuts. You will not see it. The only requirement for that is that your server is not overloaded, right? So if there would be constant requests, it will not really work. But in reality, we're all trying to design a machine which is not only responsible. This is not real-time system, right? We are not working in a real-time system. There's always some gaps which allows for some delays, some fluctuation in the system to just accommodate for it. So we actually have this situation, and this can really work for you as well. Other problem, static call graph. Static call graph is a funny thing. It's really nice. It makes small binaries. It works really fast. But it has some peculiarities. And here I'm just showing one example which I find is quite interesting to know because it's not obvious on the surface, right? What do we do here? Essentially, we're asking Julia what is the return type of a map which applies identity to the vector of int64. Well, you can't expect that we do nothing, right? We just iterate over the vector, but we don't change anything because it's an identity function, right? And the result is what we expected. What if in our vector, we don't like abstract types for the static call graph, right? But the first approach when we think about this, oh, we need to mix several types. What if I have a union of types, right? This should work really well. Let's have a look, yes. What if we have vector of union of types? Actually, static call graph is very happy about this. It understands that there's only two possibilities, so we can compile. But surprisingly, it returns union of several potential vector types, and if you look here, the vector is now doesn't have union inside, it says signed, because at a certain moment, Julia thinks, well, unions are too complicated, we need to compress them. And if you keep extending the type, then it seems, okay, there is too many possibilities, and this is abstract type, this is abstract type. Static call graph is not happy. One potential solution, I'm not saying that the only one, is if you can use tuples instead, it will really work. So tuples are much better in that case, but that's not the only way. Let's go shortly through our struggles, right? As Jorge mentioned, abstract types in a structs usually a bad idea. Functions with concrete types is not that nice for Julia or expandability. Multiple or dynamic dispatch is actually available even with a static call graph, but you need to be careful not to trigger it too much. Unions is a trick, and tuples is your friend. And there's many tools in Julia which can help you to deal with this. However, through our testing, we found that, running Julia C is more reliable. Sometimes this is hidden, but as we saw on this conference, Jet is really under development. The new versions are coming. The problems would be solved, I believe, end of this year. This is really nice. And some of the community packages are actually not compatible with the static call graph. This is the two that we were using. But we were happy to see that Julia Hub helped us to solve this problem. So a subset of HDF5 is now static call graph compatible, this subset that we use, and OM Einsam, I think, the fully compatible.
Cody, I'm still waiting for that PR.
All right, it's not yet delivered. It would be. Compilation-wise, well, we see that the binaries are really small. This is really nice. You need to still study compilation flags of Julia, because if you compile it on one platform and deploy to another platform, it will most likely not work. So please study the CPU optimization flags. But you can actually work around this. But what we actually found that because the Julia C is just Julia code and Julia C internal is also Julia code, we're actually not using Julia C.gl directly. We just learned how the Julia compiles, and we built our own pipeline, mainly because we need to inject extra meta information and do some extra pre and post processing during our build steps. But I'm just encourage you to have a look, and you will understand this much better after you have a look, and this is really small code. So as a summary, we found that Julia is feasible for our use case. We really hope that our next machines would be using Julia in control. So far, it's going well, and we're looking forward for it. However, the timing performance-wise, you can solve all the problems, and there's not so many of them. However, the user experience of using static call graph can be improved, waiting for it being improved, I hope would be improved. And of course, the third-party packages, it's much more difficult thing, because not all of them are static call graph compatible, and probably some of them will never be for various reasons. So you need to be aware of that and vigilant. If you want to deploy something, you need to start static call graph compatibility from the very beginning, not at the very end, like we did. And that's basically conclude our talk. One last sign is at 12 we have a meet and greet session here. I think somewhere there would be some food, so please join us if you have questions. We'll be happy to answer them right now, but if you have even more questions, please join us at 12. Thank you very much.
Thank you, Jorge and Yury. As they said, they are around at lunch. Please go and ask them questions. We can probably do one question right now while Bill comes and sets up. Yeah.
Thanks for the great talk. I have one question. Do you ever have a use case where Julia does need to create an object that then needs to get passed back to the upper layer that's in C and C++? And if so, how do you handle that?
So the question is, do we have a use case if Julia need to create an object which is not passed?
Which is then passed back
Which
up.
is then passed.
Yeah.
Oh, it's a great question. Yes, we do a lot, right? All the input is actually going through that road and all the output as well. But the answer would be really long. Watch my talk yesterday because I was talking exactly about that.
Thanks.
Thanks. A round of applause for Yury and Jorge, please. And do see them at lunch if you have any more questions.